Hello, welcome to this course on functional analysis. I'll be following fairly faithfully the book Functional Analysis by myself, which appears in the Trim series number 52 of the Hindustan Book Agency. So this is the book which we will be following. So functional analysis is essentially the marriage of linear algebra and analysis. We do analysis on vector spaces, and to do that a vector space needs to be endowed with a topology which has to be compatible with the linear structure. So more precisely, we have the following definition. A topological vector space is a vector space V over R or C. We will always only have these two fields with a topology such which is housed off and such that the following mappings are continuous. So xy in V cross V maps to x plus y in V for all xy in V. So this is vector addition. Alpha x in F cross V. So F equals R or C maps to alpha x in V, and this is for every alpha in F, for every x in V. This is scalar multiplication. So we need that these two mappings are continuous. So the standard example of a topological vector space is what we call a normed linear space. So this is a vector space which is equipped with a norm. So what is a norm? So V is a vector space and over R or C, and therefore a norm is a function from V to R such that for all x in V we have norm x greater than or equal to 0, norm x equal to 0 if and only if x is 0, for all x in V, for all alpha in F we have mod norm of alpha x is mod alpha times norm x. So F equals R or C, and then finally we have the triangle inequality, which is the most important. You have that for all xy in V we have norm of x plus y less than or equal to norm x plus norm y. So whenever we are confronted with the problem of verifying whether a given function defines a norm or not, the first three properties will be more or less obvious, and most of the effort, if any, would go in verifying this last statement, namely the triangle inequality. So once a vector space with a norm would be called a normed linear space. So given a normed linear space, we can define a metric dxy as norm of x minus y. So it is clear that dxy is non-negative. Dxy is 0 if and only if x equals y. Now if you have x, y and z, then x minus y can be written as x minus z plus z minus y, and therefore by the triangle inequality we get that norm of x minus y is less than or equal to norm of x minus z plus norm of z minus y, namely the distance function d satisfies the usual triangle inequality for a metric, and therefore that is why we have the same name for these two inequalities. Okay, so automatically therefore a normed linear space gets a topology defined by this norm, which is a nice metric topology, and that is called the norm topology of this vector space. So now let us see whether this norm topology makes those two functions continuous. So what do we mean? Since we are dealing with metric spaces, it is enough to check continuity via convergence of sequences. Now what do we mean by saying xn converges to x in a normed linear space V? So V is now a normed linear space. So we mean that norm of xn minus x should go to 0 as n tends to infinity. This is the definition of convergence. And so if you now have xn goes to x, yn goes to y, then you can write that norm of xn plus yn minus x plus y is less than or equal to, by the triangle inequality, norm of xn minus x plus norm of yn minus y. And by what we are given, xn goes to x, yn goes to y, so this goes to 0, so this also goes to 0, so xn plus yn converges to x plus y. So we have that a vector addition is indeed continuous. Similarly, if alpha n goes to alpha in F, the basic field, which is always real or the complex numbers, then you have alpha n xn minus alpha x. Similar, in the same way, we can, by adding and subtracting the appropriate thing, we can write this as mod alpha n times norm xn minus x plus norm x times mod alpha n minus alpha. Alpha n goes to alpha, so this goes to 0. Xn goes to x, this goes to 0. This is a fixed quantity, and alpha n being a convergent sequence is automatically bounded, and therefore the right hand side goes to 0, so that you get alpha n xn goes to alpha x. Thus scalar multiplication is also continuous, and therefore a normed linear space is automatically a topological vector space. The norm itself is a continuous function in this vector space, because if you are given two vectors x and y, by that writing x equals x minus y plus y, you get by the triangle inequality that norm x is less than or equal to norm of x minus y plus norm y, or norm x minus norm y is less than or equal to norm of x minus y. Similarly, norm y minus norm x is also less than or equal to norm of y minus x, but y minus x is minus of x minus y, and mod of minus 1 is 1, and therefore this is just norm of x minus y again. Therefore you get modulus of norm x minus norm y is less than or equal to norm of x minus y. And this is a very useful and useful inequality to remember, and this shows that the norm itself is a continuous function in a normed linear space. Okay, so once you have a normed linear space and the associated norm topology, which is a metric topology, you have sequences which are Cauchy, and if every Cauchy sequence converges, you say that the space is complete. So a complete norm-linear space is called a Banach space. Therefore, we have a vector space on which we have defined a norm that gives you a metric topology called the norm topology, and if this topology is complete, then the norm linear space is called a Banach space. So now it remains to give some examples of norm linear spaces. So I am going to give three classes of examples. The first is finite dimensional. The second would be sequence spaces. And third being function spaces. Therefore, this is a very rich class, and we will see several examples of function spaces during the course. And this, to start with, this is a good way of classifying the vector spaces and looking at the various examples. So let us start with finite dimensional spaces. So the first example. So let us just take R. So throughout, I am not going to say R or C, R or C. I will do the calculations for R, and you can easily check that the complex case is identical almost. In case there are some special changes to be made, I will then explain in that situation. So I will deal with real vector spaces for most of the time, and then you will all those results will carry over to the complex case without problem. So R is a one-dimensional vector space over itself, and we define the norm of X as the usual modulus of X. Then of course it is now trivial that all the three properties, the norm mod X is greater than or equal to 0, it's equal to 0 if and only if X equals 0, and the triangle inequality is of course well known, mod of X plus Y is less than or equal to mod X plus mod Y. And R is a complete metric space, as you know, and therefore this is an example of a Banach space. Let us take another example. This time I will deal with R2. So given any vector x, it will have two coordinates x1 and x2, and I am going to define norm x2 in this case to be square root of mod x1 square plus mod x2 square. Again, the first three properties, non-negativity, equal to 0 if and only if x equals 0, and norm of alpha x equals mod alpha norm x are all trivial from this. So what about the triangle inequality? So to see the triangle inequality, we call that norm x is nothing but the magnitude of the vector x1, x2. So if you have x here, so this length is mod x. So if y is any other vector, then complete the parallelogram, and then this diagonal here, this will be x plus y. So now it's an old theorem from high school that two sides of a triangle are in length greater than the third side. So that immediately tells you that norm x plus y2 is less than or equal to norm x2 plus norm y2. In fact, the name triangle inequality comes only from this case, because this is the generic case, and from this generalizations have been done, and therefore this shows that this is a norm. We can give one more norm on R2, say norm x equals mod x1 plus mod x2. And in this case, it's even easier to check the triangle inequality because it just comes from the triangle inequality of the norm. Now, in both these cases, if you took a Cauchy sequence xn, then xn1 will also be a Cauchy sequence. xn2, the sequence of second coordinates, will also be a Cauchy sequence. Therefore, xn1 will converge to some x1, xn2 will converge to some x2, and we denote that x equals x1, x2, and it is immediate to see that norm of xn minus x 1 goes to 0, norm of xn minus x 2 also go to 0. Because of the component wise convergence, the vector convergence also takes place. So R2 with either of these norms is a Banach space. Now we will generalize all of this, and then let us go to Rn. So example 3, let us go to Rn. So any vector x you write as x1, x2, let me write capital N here, xn. Then let 1 lesser equal to p less than infinity. Then we define norm xp is equal to sigma I equals 1 to n mod xi power p whole to the 1 by p. And I am also going to define another norm x infinity is equal to max mod xi for 1 less than equal to I less than equal to I. Now it is easy to see again that the first 3 properties of a norm are immediately satisfied. The triangle inequality is easy for norm x infinity, because if you have xi plus yi is less than equal to mod xi plus mod yi, which is less than equal to norm x infinity plus norm y infinity, and this is true for all I. So if I take the maximum on the left hand side, I get norm x plus y infinity is less than equal to norm x infinity plus norm y infinity. Therefore, this becomes a norm linear space. Now our main job, our next step, is to show the triangle inequality is true for each of these norms, which we will do. Once they are done, we see that all of these define norms on Rn. So we have an uncountable family of norms here defined, and in each case, if you took a Cauchy sequence, it automatically means that the coordinate sequences are also Cauchy. So, and therefore they will all converge, since R is complete, C is complete, and therefore component wise you will have xn I converges to xi, and consequently if I define x is x1 xn, then you will get norm xn minus x p goes to 0. These are very easy to check, and therefore our next job, our job will be complete. So Rn with any of these norms will be a Banach space, provided we have shown that the triangle inequality is true for norm xp for 1 less than equal to p less than infinity. For 1 we have already seen it. So for 1 strictly less than p less than infinity, we want to show that this is a norm, indeed a norm, which we will now do.